Hello everyone, welcome to my channel Dr. Tapati's presentation. Myself Dr. Tapati Vanjade. In this unit, we will know about the unit of enzyme activity. Then we will calculate specific activity, turnover number and catalytic efficiency of an enzyme. Along with that, we are going to solve few problems associated with specific activity, turnover number and catalytic efficiency.
Let's start with the units of enzyme activity. Enzymes are not expressed in terms of their concentrations like as mg or microgram. They are expressed only as activities. There are various methods have been introduced for the estimation of enzyme activities, and they are expressed in many ways like King-Armstrong units, Samuel-G units, Riemann-Frankel units, spectrophotometric units, etc. Therefore, in order to maintain uniformity in the expression of enzyme activities as units, worldwide mostly CATAL and international units, that is IU, are mostly used in order to express enzyme activity unit. One CATAL or one CAT denotes the amount of enzyme activity that transforms 1 mole substrate per second. Activity may also be expressed as millicatals or MCAT and microcatals or microcat and so on. Some scientists prefer to use standard units or SI units, that is IU. One SI unit or international unit IU is defined as the amount of enzyme that causes the disappearance of 1 micromole of substrate or appearance of 1 micromole of product per minute. That means one enzyme unit is equal to 1 micromole per minute. In case of cattle, it was 1 mole per second. Or we can define international unit as the amount of enzyme activity that catalyzes the conversion of 1 micromole of substrate per minute. So enzyme activity is equal to micromole of product divided by time. IU and cattle are interconvertible. 1 IU is equal to 16.67 nanocattle, or 1 cattle is equal to 6 into 10 to the power 7 IU.
Now let's calculate specific activity. What is specific activity? It is defined as the number of enzyme units per unit mass. This mass could correspond to the mass of the pure enzyme, the amount of protein in a particular isolate, or the total mass of the tissue from where the enzyme was derived or enzyme was isolated. Therefore, we can write specific activity is equal to enzyme activity divided by amount of enzyme. So, if we divide enzyme activity by the mass of the enzyme or amount of the enzyme, you will get the specific activity value. In that case, unit of specific activity is equal to mole of substrate divided by mg of enzyme into minute, or we can say unit of specific activity is equal to moles per mg per minute. Let's solve a mathematical problem for specific activity. This is the question where 1 mg of an enzyme with molecular mass 40,000 gram per mole gives a Vmax value of 20 millimolar per minute. The reaction is carried out in 2 ml. What is the specific activity of the enzyme? We have to calculate specific activity of the enzyme. In this question, Vmax value is 20 millimolar per minute. So we can write 20 millimolar per minute is equal to 20 millimoles per liter per minute. So in 1000 ml, that is 1 liter, enzyme activity we can write as 20 millimole per minute. We have to calculate enzyme activity in 2 ml because the reaction is carried out in 2 ml. So in 2 ml, enzyme activity will be 2 into 20 into 1000 divided by 1000 micromole per minute. We are converting millimole to micromole. Therefore, we are multiplying 1000 here, and we are getting the answer as 40 micromole per minute. That is enzyme activity in 2 ml. So our substrate conversion to product is 40 micromole per minute. Therefore, the specific activity, as we know that specific activity is equal to enzyme activity divided by amount of enzyme. So here enzyme activity in 2 ml is 40 micromole per minute, and amount of enzyme is mentioned here that 1 mg. So I have written this 1 mg. So if you solve this, we will get 40 micromole per minute per mg. That is the specific activity of the enzyme. Now next question is, an enzyme preparation has activity of 2 units per 20 microliter and protein concentration of 0.4 mg per ml. What is the value of specific activity? So here again we have to calculate the specific activity of this enzyme. Let's solve this problem. How? The number of unit or number of enzyme activity unit per microliter is equal to 2 by 20, because 2 units per 20 microliter, so 1 by 10 units per microliter, that is the enzyme unit per microliter value, that is 1 by 10, and the number of unit per ml will be 1 into 1000 divided by 10. So in 1 microliter 1 by 10, then in 1000 microliter or 1 ml, that will be 100 unit. We are multiplying 1000 here. We are calculating for 1 ml. Now, as you know, specific activity is equal to number of units per ml divided by concentration of protein or concentration of enzyme or protein content of enzyme. So we can write here the number of units per ml is 100. We are putting this value, and the concentration of protein is 4 mg per ml. So in 1 ml the protein content is 0.4. In 1 ml the enzyme activity is 100. So the answer is 250 unit per mg. It is the specific activity of the enzyme. Now next question is, from a stock of 5 mg per ml enzyme preparation, you use 4 microliter. The total volume of the enzyme preparation is 3 ml. You observe that our Vmax value is 90 millimolar per minute. What is the specific activity of the enzyme? As we can write, specific activity is equal to micromoles of substrate conversion per minute divided by mg of enzyme. In 1000 ml, micromoles of substrate per minute is equal to 90 into 10 to the power 3, because 90 millimolar per minute means in 1000 ml micromoles of substrate is 90 into 10 to the power 3. We are converting millimolar to micromole. Millimoles to micromoles. So we are multiplying 10 to the power 3. Now micromoles of substrate per minute in 3 ml, because the total volume of the enzyme reaction is 3 ml. So the total micromoles of substrate substrate conversion per minute in 3 ml will be 3 into 90 into 10 to the power 3 divided by 1000, that is equal to 270. And the protein content of enzyme in 1 ml or 1000 microliter is 5 mg. We have to calculate the protein content of enzyme in 4 microliter. So it will be 5 into 4 divided by 1000. Protein content is 5 mg in case of 1 ml solution. So in 4 microliter it will be 5 into 4 divided by 1000 mg, or we can write it 20 by 1000 or 0.02 mg. So total protein content is 0.02 mg. And micromole substrate per minute is 270. So we can write specific activity of the enzyme is equal to 270, which is micromoles of substrate per minute, 270 micromoles per minute divided by 0.02 mg is the protein content of the enzyme in 4 microliter. So the answer is 13.5 microliter per minute per mg. It is the specific activity of the enzyme. Let's know what is turnover number or molecular activity of an enzyme. Turnover number is the number of the substrate molecules converted to product per molecule or per active center of an enzyme per unit time, or it is the maximal number of molecules of substrate converted to product per active site per unit time when the enzyme is saturated with the substrate. You can see this figure where all the enzymes are saturated with substrate. All the enzyme molecules are saturated with substrate. So the turnover number is the maximal number of molecules of substrate converted to product per active site per unit time when the enzyme is saturated with substrate. The higher the turnover number, the more efficient an enzyme. So if turnover number is higher, so maximal number of molecules of substrate converted to product per active site per unit time will be high. It depends upon all the active points present over enzymes. Let's calculate the turnover number of an enzyme. Turnover number defines the rate at which an enzyme converts its substrate. As we know, initial velocity V0 is equal to d concentration of product divided by dt, that is equal to K2 into concentration of enzyme substrate. Here in this step we are getting the initial velocity as K2 into concentration of enzyme substrate complex. When all the active sites are occupied by the substrate, then ES is equal to ET, total enzyme concentration, and the reaction is said to be operating at the maximal velocity. Therefore, V0 is equal to Vmax. In that case, Vmax is equal to K2 into ET, where V0 is replaced by Vmax, and we are writing, instead of ES, we are writing here ET. here ET. So Vmax is equal to K2 into ET. ET means total enzyme concentration. The maximal rate of the enzyme describes the highest number of substrate molecules that can be transformed into product over a given time period when all the active sites are occupied. In that case, we can write K2 is equal to Vmax divided by E2. We are converting this equation here to K2 is equal to Vmax divided by ET. As K2 is driving the rate, because this is the rate limiting step. Last step is the rate limiting step. It is the rate limiting step. So K2 is driving the rate, and K2 is equal to K cat, that is catalytic constant, or we can write K cat is equal to Vmax by ET, because here K2 is equal to K cat. We are putting K2 is equal to K cat, that is equal to Vmax by ET. So, and K cat is equal to turnover number, that is equal to maximum number of substrate molecules converted to product per second or per unit time by each active site. Unit of turnover number is per second, and 1 by K cat, 1 by turnover number is equal to amount of time required for an enzyme to convert one substrate molecule to the product, that is the time required for one catalytic event. In that case, 1 by K cat unit is equal to S. Catalyst has the highest turnover. Catalyst has the highest turnover numbers of all the enzymes. One molecule of catalyst can convert over 2.8 million molecules of hydrogen peroxide to water and oxygen per second. Catalase enzyme catalyzes conversion of hydrogen peroxide to water and oxygen, and one molecule of catalase can convert over 2.8 million molecules of hydrogen peroxide to water and oxygen per second. Turnover number as high as 40 million have been reported for catalase. In a distant second place, carbonic anhydrase catalyzes carbon dioxide to form bicarbonate at the rate of 600,000 molecules per second. That means 6 lakhs molecules per second. Nowadays, it is a ubiquitous term focusing strictly on the catalytic center as distinct from the classical term rate of reaction, which emphasizes the generation of products or the consumption of reactants. Strictly focusing on the catalytic center, not on rate of the reaction. Let's solve a problem for turnover number. Question is 2.5 microgram of enzyme with molecular weight 50,000 gives a Vmax value of 3 micromole per minute. First of all, you have to calculate turnover number for this enzyme. Then calculate turnover number if the enzyme is dimeric with 2 non-identical subunits and trimeric with 3 identical subunits. And third question is what is the turnover number if 5 microgram enzyme gave a Vmax value of 3 micromole per minute. Let's solve it. Here Vmax value is 3 micromole per minute and total enzyme content is equal to 2.5 microgram. Here it is given 2.5 microgram. 2.5 microgram is equal to 2.5 divided by 50,000, that is the molecular weight of the enzyme. So we are converting microgram to micromole by dividing the molecular weight, and therefore the total enzyme activity, total enzyme content ET is equal to 5 into 10 to the power minus 5 micromole. Now calculate turnover number Kcat, that is equal to Vmax by ET. We already know that if we put Vmax value as 3 micromole per minute and ET value as 5 into 10 to the power minus 5 micromole, then we will get 0.6 into 10 to the power 5 per minute, that is equal to 1000 per second. We are converting minute to second here, and therefore we are getting 1000 as the answer for turnover number. So first question answer is 1000 per second. That is the turnover number Kcat. Let's solve second question. If the enzyme is dimeric with two non-identical subunits, then molecular weight of enzyme per catalytic site is equal to 50,000. Then the turnover number per catalytic site will be same 1000 per second. 1000 per second. If the enzyme is trimeric with three identical subunits, then 1 mole of enzyme is equal to 3 mole of catalytic sites. Hence, turnover number per catalytic site is equal to 1000 divided by 3, that is equal to 333.33 per second. That is the answer for question 2 if the enzyme is trimeric with 3 identical subunits. Now we have to solve third question. In that case, 2.5 microgram of enzyme with molecular weight 50,000 gives a Vmax value of 3 micromole per minute. It is given here in the question. For 2.5 microgram enzyme gives Vmax of 3 micromole per minute. When the enzyme content increased twice, if you see question 3, the enzyme content is increased twice because 2 into 2.25 is equal to 5 microgram. Again, the Vmax is the same value. The Vmax value is giving, although the enzyme content is increased twice, Vmax value is giving the same value, that is 3 micromole per minute. Therefore, Vmax per mole of enzyme will be half of the 1000 per second. Therefore, in that case, the turnover number will be 1000 divided by 2, that is equal to 500 per second. This is the answer for question number 3. Let's solve next question. Calculate turnover number and specific activity of the enzyme with molecular weight 40,000 Dalton in a reaction with Vmax is equal to 4 micromole per minute, where the enzyme amount is 2 microgram. In this case, Vmax is equal to 4 micromole per minute. Let's calculate total enzyme content, that is ET is equal to 2 microgram. If we convert 2 microgram to micromole, then we have to divide 2 divided by 40,000, that is the molecular weight. So we are getting total enzyme content as 5 into 10 to the power minus 5 micromole. And turnover number is equal to Vmax by ET. Therefore, if we put Vmax as 4 micromole per minute, and if we put ET value as 5 into 10 to the power minus 4 that we have calculated, we will get 0.8 into 10 to the power 5 per minute, or 80,000 per minute, or we can convert it into per second by dividing this value with 60. Let's calculate specific activity. As we know, specific activity is equal to enzyme activity divided by amount of enzyme in mg. So enzyme activity here 4 micromole per minute, and amount of enzyme is 2 microgram. If we convert 2 microgram to mg, it will be 2 into 10 to the power minus 3 mg. So we will get 2 into 10 to the power 3 micromole substrate conversion per minute per mg is the answer for specific activity of the enzyme. Let's know about catalytic efficiency. In order to know how well does an enzyme do its job, we have to know how well does it bind with the substrate, and it depends on Km value. If Km value is less, then binding will be better. And then we have to know how rapidly does it convert substrate to products, how rapidly it convert substrate to products, and in that case it depends on the value of Vmax. Therefore, in order to know how well does an enzyme do its job, we have to know both of the values of Km and Vmax. We get an expression which reflects both the properties of an enzyme, that is Kcat divided by Km. The ratio of Kcat divided by Km is defined as the catalytic efficiency, and can be taken as a measure of substrate specificity. In that case, K2 is equal to Kcat. Already I told that K2 is equal to Kcat. It is the rate limiting step. Kcat is equal to catalytic constant, and Kcat is equal to Vmax by ET, that is equal to turnover number. When the Kcat, so we have, if we have to calculate Kcat, we have to know Vmax value. So when the Kcat is increased or Km is decreased, you can see from this equation, if we increase Kcat value, or if we increase Vmax value, then the catalytic efficiency Kcat by Km is increased, because the catalytic efficiency is equal to Kcat by Km. If Kcat is increased, therefore the catalytic efficiency will be increased, or if we decrease the value of Km, then the catalytic efficiency will be increased. This ratio is important because it allows direct comparison of the effectiveness of an enzyme toward different substrates. What are the factors influencing catalytic efficiency? The rate of electronic rearrangements required for the formation of product. The second factor is diffusion control limit. That means how often enzyme collides successfully with the substrates. And third factor is catalytic perfection. An enzyme catalyzes a reaction as rapidly as it encounters substrate, Based on the laws of diffusion, the upper limit for such rates as determined by the frequency of collisions between substrate and the enzyme is between 10 to the power 8 and 10 to the power 9. Few enzymes actually have efficiencies that approach this range, indicating that they have near perfect efficiency. As for example, fumarase 2.3 into 10 to the power 8 is the catalytic efficiency value. Let's solve few mathematical problems associated with catalytic efficiency. First question is, A is converted to E by enzyme EA, EB, EC and ED. The Km values of the enzymes are 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 5 and 10 to the power minus 4 respectively. If all the substrates and products are present at a concentration of 10 to the power minus 4 molar and the enzymes have approximately the same Vmax value, the rate limiting step will be C to D or D to E or A to B or B to C. You have to determine the rate limiting step. So in this case, this is the reaction where A is converted to B, then B is converted to D and D is converted to E. Rate limiting step means the slowest step. Already I mentioned that the rate limiting step is the slowest step, and slowest step means lowest catalytic efficiency. Catalytic efficiency is equal to Kcat by Km. So hence catalytic efficiency is inversely proportional to Km. If Km value is high, then catalytic efficiency will be low. When Km value is highest, that means catalytic efficiency is lowest, and that step is the rate limiting step. So we have to find out the highest Km value in order to get the lowest catalytic efficiency, which is the rate limiting step. If you see the question, you will find that 10 to the power minus 2 is the highest Km value. So first step is the rate limiting step because it has the lowest catalytic efficiency. In this experiment, 10 to the power minus is the highest value of Km, and therefore the answer is question number 3, that is A to B. First of all, we have to find out Vmax for the enzyme. In this question, V0 value is 65. Here you can see in the question V0 value is 65.0 micromole per ml per second. Km value is 3.0 into 10 to the power minus 4 molar, and substrate concentration is 160 micromole. Here it is mentioned substrate concentration 160 micromolar. We have to find out Vmax value. As you know, the Michaelis-Menten equation is V0 equal to Vmax into substrate concentration divided by Km plus substrate concentration. So from this equation we can find Vmax is equal to V0 into Km plus S divided by S. If we put all the values in this equation, we will get that 60 micromole per ml per second, that is the value for V0, into Km value is 3.0 into 10 to the power 4, 10 to the power minus 4 molar, plus 160 micromolar, 160 is the substrate concentration, divided by substrate concentration, that is 160 micromolar. Or we can write this equation as 65 micromole per ml per second into 3 into 10 to the power minus 4 into 10 to the power 6 micromolar. We are converting molar to micromolar by multiplying 10 to the power 6. So we are getting 186.9 micromole per ml per second. That is the answer for Vmax. Let's solve second question. What is the turnover number for the enzyme under the same condition? As we know, turnover number Kcat is equal to Vmax by Et. That is it. If we put Vmax value as 186 and Et as 3 nanomole per ml, as it is mentioned in this question, Et is 3 nanomole per ml. So if we solve it, we will get, we are converting nanomole to micromole by multiplying 10 to the power minus 3, and we will get the final answer as 62,000 per second. That is the value for turnover number. Let's solve question number C and D. What is the catalytic efficiency for the enzyme under these conditions? And we have to mention, does the enzyme display catalytic perfection under these conditions? As we know, catalytic efficiency is equal to Kcat divided by Km, and Kcat value already we have calculated, that is 62,000 per second, and Km value is given in this question, that is 3 into 10 to the power minus 4 molar. If we divide Kcat by Km, we will get this value. So 20.67 into 10 to the power 7 per molar per second. That is the catalytic efficiency, or we can write it as 2.067 into 10 to the power 8 per molar per second. You can see that the power of catalytic efficiency here is 10 to the power 8. Already I have mentioned that based on the laws of diffusion, the upper limit for such rates as determined by the frequency of collisions between substrate and enzyme is between 10 to the power 8 and 10 to the power 9. So the catalytic efficiency is greater than 10 to the power 8. If you see this equation, the catalytic efficiency is 2.067 into 10 to the power 8 per mole per second. That is higher than the 10 to the power 8 per mole per second, which is in the range that qualifies it to be considered catalytic perfection. For catalytic perfection, catalytic efficiency should be in between 10 to the power 8 and 10 to the power 9. So in this case, the enzyme displays catalytic perfection under these conditions. What determines the ultimate speed limit of an enzyme catalyzed reaction? That is, what is it that imposes a physical limit on catalytic perfection? When an enzyme is catalytically perfect, the reaction rate has become dependent on the rate at which substrate is able to diffuse into the active site. This rate places an upper limit of 10 to the power 8 per mole per second to 10 to the power 9 per mole per second on the catalytic efficiency of an enzyme catalyzed reaction. Beyond this, there is nothing that evolution can do to further increase the rate at which the enzyme catalyzes the reaction. So, the catalytic efficiency value should be within 10 to the power 8 to 10 to the power 9 molar per molar per second. Thank you very much for watching this video. Kindly like, share and subscribe this channel. Don't forget to press the bell icon to get the notification for new video.